So welcome back everyone to the second part of the morning to continue on the theme of applications of AI. I'm very happy to welcome Violet Snell from Jenoptik, who's going to be talking about applications in vision. So,
thank you very much, Mark. Hi everyone. So my name's Violet Snell. I'll just briefly explain who I am and what I'm doing here and why I was invited to speak to you. I'm essentially an engineer. My background is in the broadcast technology industry. I spent over a decade doing both research and development on things like image processing algorithms, mostly on video, so not just a single image, but a sequence. Developing compression algorithms, so things like MPEG-2 I used to work on, and motion estimation, so that's telling which parts of the picture are moving at what speeds, and hopefully try and recreate intermediate images so that you can translate video programs from, let's say, an American TV standard to a European one that runs at a different rate. And you have to do all of that in real time. So you end up having massive boxes of humming electronics, custom designed to try and keep up with that quite demanding task. I also worked in software development as well, but always involving images, pixels of some kind. If it's got pixels, I will do it. But eventually I got bored of that stuff, and I came here to CVSSP to do a doctorate in computer vision. And this time I was working on medical images, so microscope scans of tissues or cell samples. And you're trying to use machine learning to work out whether there's a particular type of disease, whether the cells are good, bad, or indifferent. So you're looking, oh, can I see? Yes. So you're looking for the little yellow circles of this is a particular type of cell that tells you how fast the tumor is growing. So medical applications of computer vision with quite a variety of different machine learning techniques, because this was the time before deep nets really kicked in. And then when I finished that, I spent a little bit of time mooching around universities as a lecturer, found that thoroughly unpleasant, and have returned to industry and been happy as Larry ever since. So I now work for Jenoptik Traffic Solutions, and I lead a team of AI researchers, machine vision researchers, all the way from very experienced postdoctoral folks like myself to undergraduate interns that the University of Surrey very kindly provides us with. And our latest intern, a master's student from here, started only 2 weeks ago. So we're always on the lookout for good people who are interested in doing this stuff. So what is the stuff that we're doing? So Jenoptik Traffic Solutions does traffic cameras. Speed cameras, don't go boo, okay? They're good for everyone, really. They started out life in this country as computer recognition systems back in the 80s, and were a founding member of BMVA, British Machine Vision Association. Anybody heard of it yet? Yeah. And have actually been collaborating with CVSSP going back to very early days of CVSSP in the early 90s and the late 80s. But about 5 years ago, they were acquired by the Jenoptik group as part of their Traffic Solutions division. So the bigger Jenoptik group is a stock market quoted multinational, mostly based in Germany, and anything to do with optics are the sort of things that we're involved in. So we have lots of fingers and lots of pies. We have divisions that do lenses and lasers, that do automotive, production automation, that do safety systems. That's ourselves, because the purpose of the traffic cameras is to keep the roads safe. And we employ about 4,500 people worldwide, so cozy. But our UK bit is nice and small and very friendly. So the things that I want to talk to you about fall into sort of two categories. One is a broad overview of machine vision tasks in general and how you categorize them. And then a few examples of the sort of things that we have done and how that maps onto the different vision tasks where they're involved. There'll be quite a lot of deep learning, if you like that sort of thing. Okay? So, if we look at machine learning tasks in general, you can really define them by two things. What is the input that you are able to provide to them, and what output you want. And the bit in the middle of how you do it is kind of immaterial at this stage. What we're trying to categorize is the task. What are you trying to achieve? So if your task is creating a chatbot, then your input would probably be text, some kind of sequence of characters, and what you might want on your output side might be annotated text parsed for what does it all mean. It might be straight the output of what the chatbot should say back. If we're talking about vision tasks, which is my field of interest, then the input most likely will be, will be an image of some sort or a sequence of images. But the output could be quite varied. So it could be a categorical output, a class label of some kind. It could be positions, masks, it could be other images, or it could be text. It could be a description of the scene. So what defines a task, a learning task, as a vision task is that the input is going to be visual, probably. Okay? So I'll go through some very common examples of vision tasks so that you get the hang of it, and then we'll see how these might be done. So the simplest one that everyone must have heard of is the classification task. So the input is an image which to you looks like a picture, but to a computer is actually a series of dots. And they're not even dots, they're numbers that tell you how bright each dot is. So if you line up numbers in rows and columns, what you get is a matrix, or if you want to be very proper, a tensor, if you like that sort of thing. So for a computer, it is entirely non-trivial to go from a very big pile of individual numbers to some kind of semantic, meaningful understanding of what do they all together represent as an object. So object categorization, until recently, was a very challenging task. And what typically is the setup for a classification task is that you have a set of predefined possible labels. Your machine needs to be able to recognize cats, dogs, airplanes, and boats. If you give it a cherry, then it's anybody's guess what the answer will be. Okay? So you have a predefined list of categories, and you're asked to pick one. Which one represents best that one object that you see in the image? Okay? There's a restriction of one on that side and one on that side. So we move up a gear into the next very common visual task, which is object detection, which is essentially a game of where is Wally. You have an image with lots of potentially similar objects, and you're trying to locate all instances of the objects of interest. So to bring it a little bit closer to home for me, you have this time two objects of interest in your input image, and what you're asked to produce is the bounding boxes, I think I've got a slightly more zoomed in version, so that you're looking for the bounding boxes of the object of interest, each box with an attached category label. So if there was also a motorbike, there'd be a different colour box and it would say motorbike. Okay? So you've gone from one label for one object to multiple instances, and you've made the task harder. However you're going to perform it, the task is inherently more difficult. But you still have a fixed list of what kind of objects you're looking for. Okay. The next upping of the ante is segmentation. So you're still giving it a single image, but rather than boxes that enclose particular types of objects, you're asking for an answer of category for every single pixel in the picture. So in this example, you've got a mask that says this is road surface, there are cars, there are pedestrians, there's sky at the top, there's some buildings. So you have, in this instance, example, it's called semantic segmentation. So all the buildings are in one lump, all the cars are in one lump. There is also a harder version of that task, which is instance segmentation, where you have to give a pixel-wise boundary between one car and the next, even if they're touching. Okay? So you're trying to separate individual objects, but gives them very precisely delineated boundaries. And so the way you assess how well you're performing at this task is not just, is my position of the edges about right, but all the way along the edge you get a single pixel wrong, that already counts against you. So it's a harder task than object detection. Does that make sense? Okay. And then move on to video. So your input is no longer a single image. Your input is now a sequence of images. In my case, you can't see them very well because they're infrared, but I'll show that video again in a sec. They are vehicles approaching an infrared camera, which is why you don't see most of the vehicle and just see the number plate. And your task is to not just find the objects of interest, which in our case are the number plates, but to find where that exact object was also present in the previous frame and the one before that, and construct a track, so that's your coloured lines here, of all the positions that this object has been in the past, where you saw it before in the earlier parts of the video. So we're still saying absolutely nothing about how you're going to achieve this, but that is the task before you. And then there's a whole bunch more different visual tasks that some of them Njong mentioned earlier. So there is anomaly detection, just to pick an example that's a bit different and interesting. So your input side is still an image, and your output side is highlighting on the right here the parts of the image that don't conform to some normality. So this is an example from a project in one of our divisions where they're inspecting screws on a production line and they want to spot any broken ones. So as long as you put in a normal looking screw, it all comes out lovely. But if there are some broken bits, then they get highlighted as an anomaly. That's not what it should look like. And you do this using, in our case, a deep convolutional autoencoder that says if it was normal, it would look like this, which is the middle images. And you compare what it really looks like to what a normal version it thinks would look like, and you spot the differences. Anomaly detection is quite different from most visual tasks that you come across, because rather than learning it from a set of examples with known correct answers, you're learning it from just an understanding of what is normal. You don't have to give it any examples of wrong ones. It just says this is the boundary of normality, and anything outside of that I will reject. Another type of visual task is facial recognition. CVSSP is world renowned for facial recognition expertise. And again, your input is an image, but your output is the identity of a person, or it might be a pair of images, and you need to say whether they're the same person or not. Gesture recognition is also practiced round here. So if you're controlling some kind of device using finger gestures, there'll be a camera looking at it, and that camera needs to quite quickly process the video of what the hand is doing and come out with a flag that says, oh, that was a pinch and that was a wave. Okay, so that's just another different type of visual learning task. Enjong talked about retrieval, so you now know what all that is about. But again, it's an application that's of interest to us. The input is an image, the output is potentially a list of other images from some kind of database that are most similar to your query image. And finally, the one that's closest to my heart these days is optical character recognition, which we need to read the number plates. So again, your input is an image, your output is a series of characters that are written within that image somewhere. And the characters might include both numbers and letters. So I'll take you through briefly a sort of system overview of automatic number plate recognition as a pipeline. So this is one of our cameras, and the bit in the middle is a set of infrared LED illuminators that shine at the approaching traffic, and all the imaging is done in infrared. So you're seeing the number plates because they are reflective, just like road signs or cat's eyes. They shine the light straight back at the source, unlike normal surfaces that bounce it off at the same angle as it was incident at. And we can do two things with the number plates once we've read them. We can either combine it with a radar and say, this number plate was going this fast, let's send them a ticket. Or increasingly commonly and more effectively, you can have two cameras and they time exactly when they saw a particular car passing at each end of a stretch of road, and the careful timing allows them to work out the average speed across a section of road. And it's more effective because people don't just slow down for the camera. People actually stay at a safer speed all the way through the section. But whichever way you're doing it, you're going to need to read that number plate, because you're going to need to know who the baddie is. Okay? So, how do we go about reading the number plates? We start with detection. So that's a video detection task. And then once we've found our number plate, we use optical character recognition to read it. So, step one. In this particular case, let me play a video. There's a video. I have to press a button. Ta-da. There you go, they're driving now. So, in this particular case, we have an embedded device. So the camera is a bear of little brain. It doesn't have a lot of processing power. So we have to use what's called a very traditional computer vision method in order to find where the number plates are within the image. So you start with convolving it with certain filters that are handcrafted rather than learnt, that respond to images that look like number plates, that have black letters on white background. And when you find the red spot, the maximum of where it's strongest, you take a little box around there and you go, that's probably where my number plate is. And then, do you want to see that again? Come back, no. No, doesn't want to see it again. And then when you've tracked them all the way to the end and the car has disappeared off, you go, well, I've got a complete track now. I will now read what it said on the number plate. So I've got my little box. I know where the number plate is. That's the bit I need to read. I can throw away all the rest of the picture and we get onto the actual number plate reading part, the OCR. So this is how it used to be done until I came and did it differently. The traditional way of doing number plate recognition goes like this. You segment each character. You put each character in its own separate box. You go, I've got sort of connected up dark bits. That's probably one letter. And then I've got a bit of a space and some more dark bits. That's probably the next letter. And you put each letter into its own box. If for whatever reason you've got a bit of dirt there and they sort of join together a bit and you get your boxes wrong, you've lost it. You'll never get the right answer now. Okay? So that's pitfall number one. Then once you've put each character in a box, you try and read each one on its own. You go, I've got a little box, it's got a letter in it. What letter is it? It's a letter A, good. Move on to the next one. That's probably a D, provided it's in focus. Might be an O, not sure. You come to the next one, you go, oh, is that a 1? Or is that an I? Oh, anybody know? It is, if it's a UK number plate. If it's a Northern Ireland number plate, on the other hand, it could very well be an I. And the complexities of it, and it would look completely identical. There is no difference in appearance. So if you knew that it was a UK number plate, you could reasonably sure say, oh, that's a 1, and move on. But you're starting to see some ambiguity there. Because the next step you need to do is to determine what's called the syntax, which is how many letters did I get, and how many numbers, and in what order did they come? Because from that, you can tell what country did the number plate come from. They tend to have patterns of 2 letters, then 3 numbers, etc. If you got your 1 and your I wrong, you'd probably get the country wrong now. But hey, you got there, you got an answer, you decided it was UK, and it all took you probably quite a long time because you had so many separate steps. Okay? So then you throw in some reality. And the reality is that the number plates are commonly covered in dirt. I think this was some snow days last year. They are often poorly lit, not very well visible, and a human would struggle to see what those said. For example, this one here, if you tried to break that up into separate boxes for each character, you've lost it. Okay, no chance. You also have number plates that go over 2 lines, which creates additional complications. You can't just go reading sideways. And there's a sort of interconnect between, is that first character an O or a 0? If you know it's a UK plate, you'll know it's an O. If it wasn't a UK plate, it could very well be a 0. So you're kind of in a bit of a bind. So we throw the whole thing away. Okay? Throw the whole thing away, and we bring in a deep convolutional neural network. Bit of a special custom one, not one that you'll see in the published papers a lot in terms of its architecture, because it's trying to do a specialist task. But in essence, it's very simple. You give it a massive pile of examples for which you know the right answers. Okay? In the case of our European data set, it's pushing 1 million, a big pile. You stick it into a beefy GPU server, burn some teraflops, and you train up a deep neural net. And then you take that neural net and you stick it inside the camera, which has very little brain, but just enough to run, not learn, but run a neural net every time a car goes past. And you're done. Okay? Easy? Not quite that simple, but sort of. So what really happens is that you get your data set, let's say for some new country that you've not done before, and it might be tens of thousands of examples, and you start by labeling it with some traditional method, because getting a human to sit down and do this 30,000 times would take a long time and they'd make a lot of mistakes. But the traditional method will also make a lot of mistakes. It's just a lot quicker than the human. And so you've got this data set that you know contains errors in the labels. And if the network you're trying to train is from time to time told porkies, when the picture has a W and it's told it's an M, it's going to get confused. It's not going to be a very good network. Its performance in terms of accuracy is not going to be fantastic. So what do? Well, you train it anyway, and then you look for the examples where it disagrees with what the training label says. You hope that it's seen enough M's everywhere else that when the label is wrong, it will disagree, and you, the human, will be able to double check it and go, oh no, that label's wrong, I'm correcting that. And once you've corrected enough of those and your data set has become cleaner, so the labels are actually correct more of the time, you're able to go around and train a better network. That better network is a lot more choosy, it's a lot more particular, it's seen more good M's and fewer rubbish ones, and it's more sure of saying, I now disagree with that one as well, you better go check that one. And when you've gone around this enough times, depending on how many were wrong to begin with, you arrive at a data set that is clean, but has only been seen by a human in a relatively small proportion of cases. So you have managed to label a large data set to a high level of quality using a small amount of resource, of human resource. And then there's some other tricks you can play. So for example, most of these look like they're about in the middle of the image. Actually, some of the time they will appear somewhere off to the side, and if the network hasn't been trained to how to read things that are off to the side, then it will fail. It won't produce the right answer. So you take the images you've got and you modify them in some way so that slightly different versions of them also appear in the training set, and the network learns more variations of the same data set. And then for the ultimate, in the ultimate performance, you take the network you've trained and you stick it back out on the road and you collect some more data and you just look for the ones where it struggled. So you have an output from the network that tells you its confidence of its answer, and if it's low you go, well, I better check it. And that gives you a precision that you're not going to obtain in any other way. And if you do that, then you get results with a lot of 9s in them. Okay, so these are, on the left is our European network. I pulled out some example countries, and where we have a considerable quantity of data, so places like UK, Belgium, Netherlands, you're talking about accuracies of over 99% in terms of the correctness of the entire string, every single character in it, and 99.9% in terms of determining which country it came from. But if you look at somewhere like Spain, where we have only a relatively small amount of data available, you see that your accuracy is starting to drop. So you're down to only 96%. If you look at Portugal, where we have really very little data, it's dropped severely, and that's below what we would consider usable. So this relationship between the size of your training set and the performance that you get is very pronounced when you're using deep learning. You do need a lot of data. There are tricks you can pull, but the more the merrier. And then on the right, you've got some of the US states that we cover these days. And for comparison, typical figures in the US of traditional methods could be as low as 60 or 70%, just because US plates are more difficult. So in the industry, that's perceived as nothing short of miraculous. Okay, and you're talking fractions of a percent as an error rate. So that's what we do for character recognition. For a bit of light relief, I'm going to look at something completely different, but also involving vehicles. So if we've also taken a picture of not just the number plate, but the whole vehicle as it was passing the camera, we can determine its class. So you're going back to the simplest form of a visual task of classification, where you're given a little crop of just one vehicle, and you're trying to determine whether it's a car or a motorbike, whether it's a van or a lorry. One of the reasons we do this is that in many places different speed limits apply to different types of vehicle. So vans and lorries are not allowed to go at full tilt as cars are in certain places. There are other places where heavy goods are prohibited altogether, and if you spot any going through there, then they get prosecuted as well. But it being an industry application, we're not just doing a little study, we have requirements. And our requirements are that this thing works any time of day. So down here, you really can't see very much of that vehicle apart from the headlights. It's starting to get quite difficult to tell whether that's a biggish car or a smallish van. How are you going to know? How are you even going to label that data set? So we use a DVLA lookup. So we look up in the government registration database what the registered class of the vehicle is, and then you know for sure that that one is definitely a car. But that guy up there is not an SUV. No, that's a goods vehicle because he's got a load bay in the back. And just looking at it, you might not always be able to tell as an untrained human. So we avoid untrained humans, and we use a registration database to get our data set right, whatever time of day. We need to be able to do this for both front views and rear views. We need to, again, run this on a small embedded device at the roadside with limited power and limited CPU. And we still need to do it quick. And of course, we need to do it as accurately as we can possibly manage. So what we did, I'll explain some of those things. So an added challenge is that most of the things you see on the road are cars. And in terms of your data set and your training process, that's bad, because you've only got very few examples of other categories like lorries and motorbikes. It makes them more difficult to learn. This guy, you know, is a van. This guy, anybody care to guess? So because we have labeled it with a proper registration lookup, if you look at the top there, it says LGV 96.7%. So it's pretty sure that's a van. I've double checked it, it is a van. Okay. So it learns the little cues that you and I might not be aware of, but it's seen enough examples of vans in the night that it can be pretty sure of what the right answer is next time. The network that we use for this is a modified AlexNet. So I think Enjong mentioned there's one of the earlier image classification networks. So it was originally designed for the ImageNet challenge, which has 1,000 different categories. We only have 5. So we do a little bit of what's called network surgery. We strip away the last layer and replace it with a new one that's a bit smaller, because we only want 5 possible answers. We don't want it confused with cherries and boats. Okay? And then the rest of it is still a bit overkill for only determining 5 classes. Its brain is a little bit too big for its own good. It thinks it knows everything and gets oversure. So we replace the other ones with smaller layers as well, so that it's able to learn a more general concept of what a car looks like, rather than remembering all the different cars it saw in the training set. We force it to constrain its representation to make more general concepts of the features that it's looking for. And after that, we get pretty good results. So it does work day or night. We get an overall accuracy of high 90s. It varies from class to class. So for cars, which we said there was a lot of, it's very good. For motorbikes, which are very distinctive, it's hard to confuse a motorbike with anything else. It's very high, even though we didn't really have enough of them. For some of the other bits, it's like goods and cars, it gets a bit confused. One man's van is another man's multi-purpose vehicle, so you get slightly low accuracies there. Oh God, get rid of that. Otherwise it'll annoy me. Go away, go away, go away. No, apparently not. Oh well, I'm nearly at the end. So for free, we get a direction classifier because we did both fronts and rears. We can also, off the same data set, train a classifier that will tell you whether the vehicle in the picture is facing towards you or away with less than 1 in 1,000 errors. So that's quite handy. So what have we seen? We've seen a variety of different visual tasks, and I think it's quite helpful to understand in more general terms how the tasks form a hierarchy of difficulty regardless of how you're going to perform them. But we've seen some of them performed with deep neural nets, woohoo. If you needed more proof, deep learning really does work if you can give it the data. So we're very lucky, as we're the owners of the sensor device, the manufacturers of the sensor device. We collect our own data, we control our data collection, and that actually enables us to produce some very good performance. But the requirements in industry are quite challenging, more so than they tend to be in academia. And I've not really had time to go into them, but there is a vast range of other things that you can do with machine vision methods. Ori, who's our latest master student, will confirm I have a long list of projects that we would like to do but haven't yet got round to, most of which involve deep neural nets in some form. And the application field elsewhere is absolutely enormous and in very strong demand. So you're definitely in the right room.